Hey guys, welcome to question 3 for the 2012 NCEA Level 2 Physics exam. And I'm going to be going over question 3 now, okay? The elastic rope, okay? In the second part of her act, Hannah flies through the air and lands on an elastic rope, which is held under tension between two supports as shown in the diagram below. Name the main energy changes that occur as Hannah is falling and as she is coming to a stop, okay? So when Hannah is at the top, right, she has a certain amount of gravitational potential energy, okay? And that gravitational potential energy will be converted into kinetic energy as she falls down, okay? It's important to remember that. So when she has gravitational potential energy, it's going to be converted into kinetic energy as she moves down, okay? Some of this energy will be lost to sound and heat energy, but that's not the main energy conversion. The main energy conversion is always from gravitational potential energy to kinetic energy, okay? And that's as she is falling, okay? You probably should have covered this in level 1. So it's gravitational potential energy to kinetic energy. I'm just going to write PE instead of potential energy because I don't have enough space. In the exam, you'll write gravitational potential energy, so the markers know what you're talking about, okay? So don't take this as an example of slacking off, okay? Always write the full thing, okay? The only reason I'm not writing the full thing is because I'll run out of space, okay? Okay, gravitational potential energy becomes kinetic energy. Once again, I'm only going to write the E, but in your actual exam, write kinetic energy out full, okay? Don't be lazy like me, okay? Okay, so when it's stopping, so when Hannah lands on the rope's gonna stretch by a certain amount of distance, and because it stretches by a certain amount of distance, there's a certain amount of elastic potential energy that is stored in the string, and that is released and converted back into kinetic energy when the rope bounces back up. So you know when you're on the trampoline, right? So you're gonna jump on the trampoline, and then the trampoline's gonna go down for a moment, and then it's gonna spring back up. So for that moment, when it's downwards, then it has a certain amount of elastic potential energy that is stored. Okay, and when it flings back up, that elastic potential energy is converted into kinetic energy again, and then the cycle just repeats when you're jumping on the trampoline. Okay, so it's just basically just kinetic energy converts into kinetic energy converting into elastic potential energy. That's the main energy conversion here. So now we're gonna write. So now we're gonna say kinetic energy is being converted into elastic potential energy. Remember to write it out full, okay? Remember. So okay, markings for this question. Okay, getting both of these correct. That means all 4 correct. That is a merit question. As a merit grade. Okay. Getting either one of these correct, so either this one, so either this one or this one, so either gravitational potential energy and kinetic energy, or kinetic energy and or 2 elastic potential energy will get you an achieved, okay? Either one of these. Alright, let's move on to the next question. Hannah doesn't like the rope to be too tight when she lands on it, okay? State the direction of the force on her from the rope. Explain in terms of the force acting on Hannah. Sorry, why the rope should not be too tight when she lands on it. Okay, so the direction of force. When the trampoline has pressed down, the force is acting upwards and it's about to spring back up. So it's pretty self-explanatory. So it's just going to be we're just going to state upwards here. We're not going to write anything more because it only says state. And at the bottom here, we're going to explain, okay? So it says explain in terms of the force acting on Hannah, why the rope should not be too tight when she lands on it. Okay. This actually brings us back to our momentum topic about change in momentum and the impulse equation. So change in P equals to force multiplied by change in time, okay? So just imagine, you have to imagine this yourself. That's the key in physics, is to imagine the real life situation by yourself, okay? So imagine you have a really tight trampoline, okay? And you're jumping, and then it doesn't compress much. So it's just going to go down a little bit, and it's going to go back up a little bit. So it's really stiff. So that's the word. It's like the trampoline is very stiff. Because it's very stiff, your change in momentum is going to be stopped in a lower amount of time. You know the stopping time, right? So the stopping time is a lot lower. Because the stopping time is a lot lower, then using the impulse equation, change in P equals to F change in time. Because the stopping time is lower, and that will actually make an increased amount of force experienced. Okay. And also something I have to mention here is like it doesn't matter how stiff my rope is. I can have a very stiff rope, the stiffest rope on the planet, or I can have a really loose rope. Okay, it really in these two examples, the change in momentum doesn't change. Okay, so so I'm gonna be jumping up on the trampoline. I'm gonna reach a specific height. So then I'm gonna accelerate back down again. When I accelerate back down again, I'm gonna land on the trampoline again, and that's gonna have the same change in momentum. So the trampoline, the stiffness of trampoline, or in this case the rope, actually doesn't affect my change in momentum. My change in momentum is only reliant on on the height, okay, and how far I dropped before I reached, and how heavy I am. Okay, so I'm gonna have a constant mass, how heavy I am, and then how fast I was moving. Okay, so how are we gonna answer this question? Okay, so we're gonna be saying. We're gonna start with, okay, so if the rope is too tight, then there will be less stretching of the rope. Because there is less stretching, stretching. There's less stretching of the rope. There would be a lower stopping time. The stiffness of the rope does not affect the change in moment. So like the stiffness doesn't affect the change in momentum as change in momentum is reliant on mass and velocity. P equals mv, okay? Because it doesn't affect it, okay? So this means this change of momentum is the same. Because the stopping time has decreased, and the formula for change in momentum is change in P equals to F, so equals to F times change in T. Okay, so F times change in T, and therefore F equals to change in P divided by change in T. Because the stopping time has decreased while the what am I saying? So while the change of momentum is the same, while the change in momentum is the same, therefore the force experienced by Hannah will be increased, and therefore this may be uncomfortable for Hannah. Okay, that's your full answer here. Okay, so you have to mention the stopping time, rope too tight, and how the tightness of the rope does not affect. Sorry, I'll bring this up a little bit so you can read it. Sorry if it's hard to read, but can't really do anything about it. But you should be able to read that actually, just a bit harder. So sorry about the inconvenience. So pause now and read. So so you can understand. So this will get you an excellence grade. This should get you an excellence grade. So this answer, so this here, that will get you an excellence grade. So for excellence grade, you're going to be mentioning the rope is too tight, and this decreases her stopping time. And you're going to mention the formula, change in P equals to force multiplied by change in time. You're going to mention that a shorter stopping time will increase the size of the upward force acting on her. And you're gonna mention how the stiffness of the rope does not affect the change in momentum. So therefore, the change in momentum is the same. Okay, so you've got to mention these 4 points in order to get the excellence grade. Okay, to get the merit grade, you are mentioning if the rope is too tight. So you're mentioning that the rope is too tight. This decreases the stopping time, and this increases the size of the force acting on her. You for merit, you didn't explain how the change in momentum is constant. Okay. For an cheat, you are explaining if the rope is too tight, it will decrease the stopping time, or the size of the force increases. So any one of these two will get you an achieved, okay? But obviously, you're not really aiming for achieved. I wouldn't really say you're aiming for achieved. I'd probably say you're aiming for merit or excellence. So just keeping in mind that you need more detail and more linking of your points in order to get the merit and the excellence, okay? So just link it as far as you can, okay? So anything that's relevant, just try to talk about it, okay? Alright, sorry if that's a bit unclear, the text, but nothing really I can do about it. Alright, sorry about that. So I'm gonna move on to the next question. C, an elastic rope is suspended from a beam. It is hanging vertically down. Hannah hangs vertically down on an elastic rope. The rope is stretched 0.6 meters below its normal position when Hannah hangs from it. Calculate the elastic potential energy stored in the rope. Okay. So, in this question, Hannah has a weight force, as you can see by the arrow, it's going downwards due to the force of gravity that's pulling her downwards. Because of this weight force, the rope has stretched 0.6 meters, which means it has gotten 0.6 meters longer due to the force, okay? For example, you have a stiffer rope. A stiffer rope, and Hannah has the same weight force. Because it's more stiff, it's harder to pull, right? For example, you're pulling a really stiff rope. Like, it'll be really hard to move it, right? So that means it'll have a higher spring constant, okay? Spring constant is just like a way of saying how stiff a rope or spring is, okay? For example, you have a really loose rope, like for example, a rubber band, okay? A rubber band is really loose, so you can just apply a little bit of force. You apply a little bit of force, and it's going to stretch a lot, okay? So that means it has a really low spring constant, okay? Okay, so in this question, it doesn't tell you the spring constant, but it does tell you the compressing distance. The stretching distance is 0.6 meters, and we can use this to find the, because we have the force acting downwards by Hannah, and therefore we can use these two things to find the spring constant of the rope. And using the spring constant of the rope, we can use the EP formula for elastic potential energy, and we can find that the elastic potential energy stored inside the elastic rope, okay? So referring to your physics formula sheet, you can see that F equals to, it says equals to negative kx, okay? So keeping in mind here, okay, this is very important, you have to listen up here, okay? F equals to negative kx, okay? This negative here, but doesn't represent a negative spring constant, okay? It represents a change in direction. So for example, a spring, right? A spring's going down, it's going to push back up. It's like a change in direction. Not really, it's not really like a negative magnitude, okay? It's basically impossible to have a negative spring constant. Even the loosest spring won't have a negative spring constant. Remember, the negative there is only to represent the change in direction. You know, for example, like this vector quantities, right? The vector quantities has the both magnitude and the direction. We can just say that this is like a directional change, not a magnitudinal change, okay? And for example, you're doing two vectors, right? Vector addition. One is acting to the right, plus one is acting to the left. Or minus one is acting to the left, and you have to like flip it around. And you flip it around, you flip, kind of like directional changes, not magnitudinal changes. So basically, you can just say F equals to kx, okay? You don't really need that negative there. It's just confusing sometimes, okay? So F equals to kx, okay? So what's the weight force of Hannah? That can be expressed as F equals to mg. So basically 55 times 9.8. And that equals to 539 newtons. So now we ask ourselves the question, due to this 539 newtons force, and the rope compresses 0.6 meters, we can use these two bits of information to see how stiff this rope is, which is basically the spring constant. So we can substitute these numbers in. So we can substitute x equals to 0.6, and we substitute f equals to 539, okay? So basically, 539 equals to k multiplied by 0.6. You move the 0.6 to the other side, so 539 divided by 0.6. And that should be giving you like 898 point something, I think it was. Let me just double check. I don't want to make any mistakes here. Yes, it is. It equals to 898.33. And spring constant is measured in Nm minus 1. Do you know why? So for example, we want to rearrange this formula to find in terms of x, okay? We want to find we want to find x in terms of f and k, okay? So we want to rearrange the formula to make x the subject. So f divided by k equals to x. So that's basically saying force is measured in newtons. No, sorry, that's wrong. That's stupid. So F divided by X equals to K. That's me being stupid, sorry. Okay, so basically that's saying F is measured in newtons and X is measured in meters. It's the stretching distance. So N divided by M is K. And therefore, this can be rewritten as N multiplied by M to the power of -1, okay? So that's where the unit comes from if anyone's curious. Okay, now we have the spring constant. So that represents how stiff or how loose the spring or string is, okay? So now we're going to be moving on to EP formula. So the EP formula for elastic potential energy is EP equals to half K x squared. We found out the K with the previous formula, and we already know the X is 0.6. We'll just pin in some numbers, and we can find EP really easily, okay? So EP equals to half, spring constant is 898.33, and that will be multiplied by 0.6 squared. Okay, we're going to plug this to a calculator, and that will be giving us our answer. So that should be 161.7 joules, which equals, oh sorry, I didn't have my pen editing instructions on, so equals to 161.7, sorry, this dot is, okay, so joules. So because energy is measured in joules, okay? So here's your final answer, 161.7 joules. And getting this answer, it should be getting you an excellent grade. Like, this is pretty high level stuff. Finding the spring constant, which is here. So finding 898.33, that's a merit part. And just acknowledging that F equals mg and F equals kx. So basically just here. Yeah, that's an achieved here. Alright, so hope you understand. I know we haven't really gone over spring constants before in class, but hopefully my explanations were clear enough for you to understand the circumstances in this question. If my explanations were clear, please comment down below. Give me some constructive criticism, how to improve in the future. And I hope to see you in the next video, which I'll be going over the final question of this exam paper. Please like and subscribe. And please, nothing, please nothing. Yeah, thanks for watching and see ya. Bye-bye.